So I'd like to expand our understanding of simple harmonic motion beyond just the basic model of a mass on a spring, which of course is useful, but there are many other examples of things that follow the rules of simple harmonic motion. So let's just look for the key relationship here. We talked about this earlier, but this idea here that A is equal to the opposite, or the -1 times omega squared times x, is something that is true at any moment within the oscillation of that mass. The general form of this is to say that there's a constant times the x function times the -1 that is equal to the acceleration function. So this is sort of what we're thinking when we see this equation. Recall where that comes from. Simple harmonic motion always is a sinusoidal relationship. The way the motion can be described is always sinusoidal, meaning we can either use a sine or a cosine to represent it. So here's just a very general form of that. I've taken off the phase shift or the phase change or angle because we can always kind of rig the system by setting up the initial conditions. When I take the derivative of this, I get negative amplitude times omega, and then it switches to the sine. And then when I take the derivative of that to get the acceleration function, it goes to negative a omega squared, and then back to the cosine. And that's really the key, is that we go back to the cosine function. I can look through this result here and see that the a and the cosine is part of the original x, so I'll just replace all of that with x. And then what I'm left with is that my acceleration is equal to -1 times a constant times x. And my constant determines the rate at which this object oscillates. So the square root of that constant tells me omega. So let's see how this, again, applied to a mass on a spring, just to review, and then we're going to look at two different types of pendula. All right, so I've got my key relationship up in the corner here to always keep in mind as we go through these questions. With a mass on a spring, I can just start with F equals ma, but then for that situation, if I move the mass in the positive x direction, there is a negative force working against it that's produced by that spring. And so that's where the negative sign comes in. But of course, the value of the force, the magnitude of force, is the spring constant k times however far I've stretched it. So I can substitute negative kx for F. And then if I just solve for A, I see that this constant here relates the x position and the acceleration of this object. And so based on what we just kind of talked about, that that constant then must equal omega squared, or omega would equal the square root of little k over m. Remember that on our formula sheet, this is actually written in terms of period, but since period is 2 pi over omega, I would just take 2 pi over this, meaning I would take 2 pi times the reciprocal, and that's where we get our formula for the period of a mass on a spring. So we're going to come up with something very similar to this, except that we are going to look at a pendulum. But a pendulum doesn't move just back and forth. It actually kind of goes up as it moves back and forth. So it's more of a rotational motion. And so this relationship has to be adjusted for rotation. So we can say that instead of linear acceleration, we're going to have an angular acceleration, alpha. And then instead of a linear displacement, x, we will have an angular displacement, theta. And so this is our new key relationship if the system rotates about a fixed point. So this diagram represents a simple pendulum, just some sort of mass that is much heavier than whatever string it is that's hanging onto it. So we're going to consider the mass to all be concentrated at one point. As the system swings, the angle is considered to be changing the positive direction this way, And so there is a torque that is working against its motion, trying to pull it back the other way. What's producing that, of course, is gravity. So let me put the gravitational force in our picture. There's our mg. But this force does not point perpendicular to the L. So recall that when we calculate torque, it's R cross F to determine our torque. That cross product, we need to take into account the perpendicular relationships between R and F, and we also have to pay attention to whether the torque is positive or negative. Okay, so in our case, we're going to call it a negative torque because, again, it works against the motion of the object. As theta gets bigger, my torque is pointing in the opposite direction. My R would be the distance from the pivot point to my object where the force is being applied, so that's going to be L. And now I need the force that is perpendicular to L. Normally we took like this, automatically did like the sine of some angle, but it's a little tricky to figure that out. Here's another way of doing that. So I can take my mg and I can break it into two components. One that points along the rope, which contributes to the tension, and one that points perpendicular to the rope, which is what I'm interested in. That part that is perpendicular is the part that's producing this torque. And so if I just do a little bit of geometry, this angle theta is the same as this angle theta. And so I am interested in the side that's opposite theta, so that would be the sine. So this component here is the mg sine. So let me add that to this then. That's the force I'm going to put in. That's the perpendicular force. And you would get the same sine theta if you just did r times f times the sine of theta. All right, so now, kind of back the way we did before, so torque is I times alpha, and so I'm going to put in my torque relationship that I just derived. And then since this is just a simple mass all concentrated in one spot, for I would just use mr squared. And my r is, again, that distance from the pivot point, L. So this is going to be ml squared. No need for a half or a 12th. I don't have a shape that I'm working with. All right, so now let's do a little bit of algebra. I can see that one of my L's would cancel out, and the mass doesn't matter. That'll be important. And then if I rearrange this, I get negative g over L. I'll bring that L over to the left side, times the sine of theta is equal to alpha. So I'm pretty close. I have my negative sign. I have a constant number for a particular situation, and I almost have theta. I have sine of theta equals alpha. Well, if I restrict myself to small angles, this is something called the small angle approximation. If I restrict myself to small angles, it turns out that when in radian mode, the sine of an angle is almost exactly equal to the actual value of the angle, as long as the angle is small, like less than 5 degrees. So if we restrict ourselves to small amplitudes, then this actually becomes negative g over L theta equals alpha. So this is really technically like an approximation. But now I can go ahead and apply my idea. That means that g over L is omega squared. It relates to our rate of oscillation. And so omega over, sorry, let me do that again here. So period equals 2 pi over omega. And so my omega is square root of g over L. So I'll flip that over, and it's 2 pi square root L over g. That's the period of a pendulum, simple pendulum. But what if our pendulum is more complex? What if it's got, you know, more of a shape to it? Let's take a look at that. I know this video is kind of long. This last part will be really quick. So it's really the same exact torque relationship. So it's r times our distance But our force is now not all the way at the end of the object. It's however far away the center of mass is from the pivot point P. So remember, we call that H. So my distance away would be H, but I would still have the same force producing this torque, the perpendicular force mg sine of theta. I would think about all that mass concentrated at the center of mass. And so that means that from torque equals I alpha, we can say negative H mg sine of theta is equal to I. Now, my I can't put in a formula because it depends on what shape I have, but I will have to make sure that it's I about point P and then times alpha. So if I rearrange here, I get negative, this is usually written mgh divided by I sub P times the sine of theta, but again, we're going to make that approximation and say it's theta for small angles. That will be approximately equal to my alpha. And so to calculate the period for small angles, I can again use the same relationship. My omega squared should equal mgh divided by I sub p. And again, this I sub p, we're going to have to use the parallel axis theorem to do it. All right, so again, putting it into a period formula, period would be 2 pi over omega, so that's going to be 2 pi divided by the square root of this, or 2 pi times the square root of I divided by mgh. Now, unfortunately, this formula is not on your formula sheet, so make sure you write it down, and we'll just have to deal with it.